Richard James will continue the presentation of these tutorials with ratios and variations. Part 4. Most of the problems that remain in this section are based on direct and inverse variation. Our first problem is based on inverse variation. We will therefore take a look at the basics of inverse variation. First, if there is an inverse variation between A and B, then as A increases, B will decrease. The converse is true. As B increases, A decreases. And the relationship is written as we have it right here. And as we progress in these tutorials, we will demonstrate why in an inverse variation we have one variable on the left hand side and the other variable on the right hand side, but in fact we have, as a matter of fact, the reciprocal of the other variable on the right hand side. Also, we need to understand that the sides do not matter. That means we may have the reciprocal of A on the left hand side and B on the right hand side, as long as on one side we have the variable, one of them, and on the other side we have the reciprocal of the other variable. Then that is a way of expressing inverse variation, and we will show mathematically how it matches with everyday experience as we progress in these tutorials. We have shown in a previous tutorial that as the divisor gets progressively smaller, the quotient gets progressively larger. B is a divisor, therefore as it gets smaller in value, A will get larger in value. We also know that as the divisor B gets larger, the quotient will get smaller. This is the foundation of an inverse variation. So we have A and 1 over B. We also know that for an inverse variation, as A increases, B decreases, and as B increases, A decreases, because as a matter of fact A is related to the reciprocal of B. So let us say that we are dividing by B. If the value of B gets larger, the answer will be smaller. And we have that as a requirement of an inverse variation. As B increases, A decreases. If you do not remember, then there is your reminder. We will divide 12 by numbers that get progressively smaller, and we see that the answer gets progressively larger. So 12 divided by 12 is equal to 1, and we will divide 12 by a number that is smaller than 12. So divide by 6 on this occasion, and the answer is larger than what we had before. And if we choose a smaller number than 6, which is 4, notice that if we divide by a smaller number than 6, then the result will be larger than the previous answer. And if we continue dividing by a number that is smaller, then the answer will get progressively larger, as we have right there. That is the reason for B being in the denominator on the right hand side. According to the requirements of the variation, we expect A to decrease as B increases. And as B decreases, we expect A to increase. So there we have it. A, and this symbol means that A is directly proportional to 1 over B. Or we may say A is proportional to 1 over B, and because of the reciprocal that we have here, we say that A is inversely proportional to B. Like in any proportionate relationship, we may demonstrate that there is a factor that relates values to their counterpart, like in the previous tutorials. And I am sure that being reminded of the previous tutorial, this is the particular situation that we had to work with, in which we were comparing the times that it took a bus and also a car in completing 2 different journeys. And we had instruction and also information telling us that the bus and the car travel at the same rate on both routes. Because of the fact that they travel at the same rate on both routes, then on a particular route, say A, the times are related in the same way as on the route B, because they travel at the same rate on both routes. And this is what we have right here as the relationship between A and B, and also between the times that the bus travels on both routes and the times that the car travels on both routes. What we did also was to demonstrate that, as we have right here, if the times that the bus and the car travel on the same route are related, as we have here, that they are related, we demonstrated here that for the bus, the times that the bus travel on both routes are also related. We have demonstrated here that the times that the bus and the car travel on this particular route are related, and that they are related in the same way that the bus and the car also travel on this route. We are also showing that because of that situation, that the times that the bus travels on both routes are related, and the times that the car travels on both routes are related. This flexibility that we are making mention of is unique to direct variation, not to the one that we have right here. But as a matter of fact, we can demonstrate that there is a proportionate relationship between values of the corresponding variables for an inverse variation, as much as we can show that it exists for a direct variation. But of course, we have our exceptions, and as we progress in these tutorials, we will take note of them. Notice that for each case, the factor by which a value is related to its counterpart is the same. When a value is the same throughout, it is called a constant. In variation, a constant is usually represented by the letter K. So what we did, showing how the times, or we are demonstrating that there's a relationship between the times for the bus and the car on the same route. And they are related as follows, that if you divide the time traveled by the bus by the time traveled by the car on route A, we will get 2.25. Also, if we do the same for route B, dividing the time that the bus travels by the time that the car travels, we will get 2.25. And we are saying that the 2.25 is a value that we will get if we have the bus and the car traveling the same rate, irrespective of how many routes we use, we will get the same 2.25. Therefore, if we had another route that had another length or different length from what we have before, then if we divide the times in the same way that we have done it right here, then we would have received 2.25. We are also showing that if we say that, let us take a comparison between the times that the bus alone, just the times for the bus. For A, the time is 180 minutes, and for B, 162 minutes, which is, of course, these two times are the times that the bus alone travel. So we are looking at just the bus alone. And if we divide as we did before, we will get 1.11, and if we do the same for the car, we will get 1.11, which is, of course, another constant value. However, what we are working with right here is a direct variation. The same is not true for an inverse variation. When we are dealing with inverse variation, we have to compare or combine corresponding values of different variables. So we are highlighting those constant values because in a direct variation problem, the constant value, even if we do not calculate it, it is always assumed in the direct variation problem. And because of that, we are highlighting the constants right there. The constant is basically the most important component of a variation problem. Even if we do not actually find its value, we are making a lot of calculations that are based on the fact that there is always a constant value by which values of the variables are related. By including the constant in a variation problem, the values are not only related, but it is a way to ensure equality. Equality makes calculation easier and more logical. And we'll take a look on the other slide at what we mean when we say equality and to ensure equality, and also that equality makes calculation easier and more logical. In the first case, the constant by which the values are related is 2.25. Look at the equalities. There we have what we call the equalities, or we are saying that we can show that we can equate values when the constant is present. And I am sure that all we need to do is just look right here. What we will see is that we took 80 multiplied by 2.25 and the result is 180, as we have right there. So we have an equation and all we do is eliminate 80 by multiplication. 80, here we are dividing by 80, therefore In eliminating 80 from that left hand side, we will multiply by 80. And we do the same thing right here. Eliminate this 72 from the left hand side by multiplying by 72, and we have 162 is equal to 2.25 times 72. This is merely a transposition of the equations that we have on the right. We multiply the equations by 80 and 72 respectively, eliminating them from the denominators, and the right hand side of the equations are multiplied by 80 and 72 respectively. So we have eliminated those denominators and we have multiplied by 80 and 72 respectively, as we would have expected. And there we have the other representation of the problem, in which we have the constant right there. In the other case, the constant by which the values are related is 1.11, with those ones recurring. The equations will follow, and no doubt we have an analogy between these values and the ones that we have down here. Again, we have a transposition of the equations that we have on the right. We multiply the equation by 162 and 72 respectively, eliminating them from the denominators, and the right hand side of the equations are multiplied by 162 and 72 respectively. Therefore, it should come as no surprise that a merely proportionate relationship may be made into a more user-friendly expression, which is an equation, by including what we call a constant of proportionality. So we may, as we have it right there, convert a merely proportionate relationship to a more user-friendly expression, which is an equation, by including the constant of proportionality, because we are always realizing that in a proportionate relationship that this and its corresponding value are related in the same way as this one and its corresponding value. So if we divide this one by its corresponding value, we get 2.25. And if we divide this one by its corresponding value, we get 2.25. So this 2.25 is a characteristic of the situation that we have right there, to the extent that for any set of values that we will use for the times of the bus and the car, we will always get 2.25. Therefore, we will make use of the fact that this 2.25 is a constant, and all that we need to do is transpose this equation that we have right here, eliminating the denominator, and we have these arithmetic expressions that we have right here on the left, in which case we have each one being multiplied by the constant of proportionality, and that we will make further use of in this tutorial. In an inverse variation, the constant of proportionality is written in the numerator when declaring equality. So for that inverse variation, the constant of proportionality is written in the numerator. After the equality is declared, we may go ahead and solve the problem. For the most part, there are only a few things to bear in mind. 1. There are only 3 symbols in a variation problem, and 2 of them are always known, or we may say the value of 2 of them are always known. The unknown being only 1, because we have 3, 2 of them are known, so only 1 is unknown. The unknown being only 1 may be found by solving the single equation. Remember that if we have a single equation in one unknown, then we may solve that single equation in one unknown. The constant of proportionality, that is the third one, is usually the first value to be determined. So if we are making use of a constant of proportionality in a variation problem, the constant of proportionality is the first thing that we need to find. Therefore, a proportionality problem has 3 stages. 1. Express the type of variation, whether direct or inverse. 2. Find the constant of proportionality. Then 3. Find any other value. So express the type of variation first. Find the constant of proportionality next, and finish up by finding any other value as required. Now we have this one. Y varies inversely as x squared. We may express the inverse variation like what we have right there. Y is directly proportional to 1 over x squared, or y is directly proportional to the inverse of x squared, which means that y is inversely proportional to x squared. The constant of proportionality satisfies equality of related values, as we demonstrated on our previous slide. When we include that constant of proportionality, then we may equate both sides of the original relationship. First, we will attempt to find the constant of proportionality. This requires the substitution of the initial values. So there we have the initial values. X is equal to 2 and y is equal to 3. And of course we would have gone through previous tutorials in which we make use of substitution. No doubt substitution is returning right here, which requires that we make use of it, and a demonstration that we cannot take anything for granted, because we will not know when we will be required to use it again. So let us do our substitution, where x is equal to 2 and y is equal to 3. And what is the result? 3 remains on that left hand side. K, numerator, 2 squared is equal to 4. 2 times 2 is equal to 4. Now we will find the constant, the value of the constant, by eliminating 4 from the divisor of the right hand side, and that we will do by multiplication. So the constant is being divided by 4, so we will multiply by 4 in order to eliminate 4 from the denominator, and we need to do the same on the other side. So we are multiplying the right hand side by 4 in order to eliminate that denominator, and we keep the equation balanced by multiplying by 4 on the other side also. 4 is eliminated from the right hand side, and on the left hand side we have 3 times 4, which is equal to 12. So 12 is equal to k, and rewrite the expression with k on the left hand side. K is equal to 12. So we have found the value of the constant to be 12, as we have right there. And when we are using that variation equation in solving a problem, we use it throughout. So we do not change it. We use the exact same equation. Y is equal to k over x squared. And no doubt our template will also demonstrate that y is equal to k over x squared. But in this particular case, we will pay special attention to the values that need to be substituted. So we have x is equal to 3, and we have found the value of k to be 12. And as a matter of fact, we are attempting to find the value of y when x is equal to 3. So the value of the constant is known to be 12, and x is equal to 3. There we have x is equal to 3 and 12 for the constant of proportionality. And do not forget that we are squaring right here. And as a matter of fact, as recently as last week, we have students squaring 3. 3 squared is equal to 6. Do not forget that when we square a number, we multiply that number by itself, or we multiply two occurrences of the number together. So square 3. 3 times 3 is equal to 9. And we will reduce the fraction by a common factor of 3. So 3 into 9 is 3, and 3 into 12 is 4. So we have 4/3, 4 over 3 for the value of y. A variation equation has two variables and a constant. Usually our first job is to find the value of the constant. However, at every stage of the game, we always have two values out of 3, and we are required to find the other one. So no matter what, in a variation problem, we can always move on. We have nothing to prevent us, because we only have 3 symbols, and we always have the values of 2 of them. All we need to do is find the value of the other one. Our next problem is a direct variation problem. In a direct variation between variables a and b, as a increases, so does b, and as a decreases, so does b. We may say 1. A varies directly as b, or we may say a is proportional to b. We may also say that a is directly proportional to b, and we will write it like that. A is directly proportional to b. The direct variation between a and b is symbolized as shown. Surely, for the variation problems that we will solve, we might not see equality between the variables. This means that a may never be shown to be equal to b. Right? So, not because we have a direct variation, that means we will encounter necessarily a situation in which the value of a and the value of b are equal. And because of that, we are still not blinded by the fact that there is a relationship or a direct relationship to a value of a and the corresponding value of b. So we know that although we do not or may not see equality, that there is a direct relationship between the value of A and the value of B. Although we may not see equality between A and B. However, as shown before, there is a constant by which the values of A are related to the corresponding values of B. So although they are not equal, that does not mean that we cannot have equality. We can have equality because we can show that there is a constant by which A, and we have done that already, by which the value of A is related to the corresponding value of B, and that constant is what guarantees or assures equality. N varies directly as V squared. Express the direct variation. So we have it right there. M varies directly as V squared. The constant of proportionality assists in attaining equality. So we need equality, and the constant gives us that opportunity, because when we have the equality, the expression is, as we said before, more user-friendly. Substitute the initial values in the equation in order to find the constant of proportionality. Initially, for a variation problem, we are given initial values. Say m is equal to this one, which is 2, when v is equal to 3. And we use those initial values in order to find the constant of proportionality. So, substitute those in the direct variation problem. Notice that we have m is equal to some constant times v squared. That is our equation. And we need to make a substitution in order to determine the value of k. So we have progressed appropriately by making the equation into a template in order to accommodate those known values, and no doubt we will have k as the unknown in the end. So m is equal to 2 and k is equal to 3, and we are squaring. Here we have the square. So 2 is equal to k times the square of 3, or 3 squared. 3 squared is equal to 3 times 3, and that is equal to 9. K is multiplied by 9 on the right hand side, as we have right here, k times 9. We will eliminate 9 by division because it is multiplied on that right hand side. We need to find k, eliminate that 9 by division. But we cannot divide by 9 on one side alone. We have to keep the equation balanced by dividing by 9 on both sides. And there we have it, the 9's gone from that right hand side, and we have on the left hand side 2 divide by 9. 9 is eliminated from the right hand side, and on the left hand side we have 2 divide by 9. So 2 over 9 is equal to the constant k. So rewrite the expression with k on the left hand side. We have k is equal to 2 over 9. We will continue to use that same variation equation, because as long as we have started and we have obtained our equation, we use it in every single step of the way, and we will have at every single step of the way at least 2 of these 3 values, and all we need to do is find the other one. On this occasion, we are attempting to find the value of m when v is equal to 6. We also have the value of the constant of proportionality, k is equal to 2 over 9, that we tend to neglect sometimes. After finding the value of the constant of proportionality, when we progress in the problem, sometimes we do not remember that we have the value of the constant, and we are spinning around aimlessly sometimes. But do not forget that the initial values are used to find the constant of proportionality, and when we have found the constant of proportionality, we use it constantly. So m is equal to kv squared, which is a template awaiting the known values of v is equal to 6 and k is equal to 2 over 9, and then we may simplify. Do not forget, here we have 6 squared. 6 squared is equal to 36. And what do we do next? Reduce the fraction by a common factor of 9. 9 into 9 is 1, and 9 into 36 will go 4 times. No doubt 2 times 4 is equal to 8. After finding the value of k, the solution of the rest of the problem may be simplified to substitution, transposition, fraction reduction. And it may be that we do not use all 3, but one or the other, or any combination of the 3. But we will have only substitution, transposition, and fraction reduction. We cannot have anything else. On the next slide, we will solve this problem by making use of ratios, or the proportionate relationship between corresponding values. Using ratios has the potential to simplify a variation problem. As a matter of fact, they may be used in greatly simplifying many problems, because I've seen some very, very tough mathematics problems, and we have gone all the way back to the simplest thing, ratios, that very simple mathematics device. We have used that very simple mathematics device to solve some of the most complicated problems, and no doubt we may use ratios in solving this problem also. We have variables m and v. M is equal to 2 when v is equal to 3. And why do we have 3 squared here? Because remember that m varies with v squared, or the square of v. So m varies with v squared, and that is why when we put the value of v, we need to square it. V is equal to 6 and m is unknown. So we have the variables m and v. M is equal to 2 when v is equal to 3. Remember that v squared, so we square the value, we square 3. Then we will square the other value for v, which is 6, and m is unknown. Right, in this particular case, we call the unknown value x. In each case, the value of m is related to the value of v squared in the same way. So, because we are talking about a variation problem, any value and its corresponding value are related in the same way as this one is related to this. So 2 over 3 squared is exactly the same as x over 6 squared. Now, we need to organize our equation saying that this one is equal to this one. But when writing an equation that involves fractions, the best way to demonstrate this is to, or the most efficient way of expressing it, in order that we may solve the problem in the least possible number of steps, and as a consequence, the shortest possible time, what do? We write x in the numerator, or the unknown in the numerator, on the left hand side. So do not forget that when we are writing an equation that involves fractions, we may write the unknown in the numerator on the left hand side, and that is the most efficient way of expressing that. So there is our equation, x over 6 squared, and do not forget 6 squared is 36, and 2 over 3 squared is equal to 9, and eliminate 36 by multiplication, because we have x that we need to find, and it is being divided by 36 on the left hand side. Therefore, we need to multiply on that left hand side by 36 in order to eliminate 36 from the denominator. But we cannot do that to one side of an equation. We have to keep the equation balanced by multiplying by 36 on the right hand side also. We do that on both sides. So see, 36 will be eliminated from the left hand side, and we have x is equal to 2 9s times 36, and we will reduce by a common factor of 9 into 9, 1, and 9 into 36, 4, and there is our answer, 2 times 4, which is equal to 8. And we will go again, solving the problem by relating values of the same variable. So whereas on the other slide, and no doubt we will make use of this relationship, we will mention it in explaining a few things on subsequent slides, that we will relate, as we have it here, a variable, or the value of a variable, which is m, and its corresponding value for v. So we have the value of m and the corresponding value for v, and that is what we have done here again, the value for m and the corresponding value for v. But we are showing also on this slide that we may not only relate a value and its corresponding value in the other variable, but we may relate values of the same variable. So we are relating the 2 and the x, and the 3 squared and the 6 squared. So we are related the two values of m. Then we are relating the two values of v. Whereas on the previous occasion, we show the relationship between m and the corresponding value of v. So there we have it. X over 2 is equal to 6 squared over 3 squared. And then we will solve. Eliminate 2 by multiplication. There we have it. 2 will be eliminated. Remember that we have, on that left hand side, we are dividing by 2. We need to find the value of x. So we need to eliminate the 2 that we are dividing by. And we will eliminate that 2 by multiplying by 2. But cannot do it on one side alone of an equation. We have to do it on the other side of the equation also. And when we have done that, the equation will be balanced. That means the equation that we have right there and the equation that we have right here are actually the same equation. Multiplying both sides of an equation by the same value does not change the equation in any way. Well, changes its appearance, but does not change it in terms of its logical components. Reduce by common factors of 9. That's what we will do now. 9 into 9 is 1. 9 into 36 is 4. Two times 4 is equal to 8. After seeing how quickly a variation problem may be solved using ratios, one might not want to use equation again. Also, we have the additional flexibility of relating the values of the same variables or corresponding values of variables. We may relate the ones that make life easier. The greatest advantage that ratios have over equation is that by using ratios, we eliminate the additional phase of having to find the constant. So we may use the proportionate relationship among the values in solving the problem, as we have done here and on the previous slide, or we may use an equation. And we are saying that when we use the proportionate relationship between the variables or between a value and its corresponding value, then we do not have to include the constant, although the constant is assumed. For sure, the constant is assumed, and we will demonstrate that on a subsequent slide. But that greatly reduces the difficulty of the problem. The constant may have been written on the other side of the equation. So what we are saying also is that when we are solving the direct variation problem, or any variation problem for that matter, the constant that we wrote accompanying v squared, we could have written the expression with the constant on the other side, like that. So now we have the constant on the left hand side. Let us see what happens. Because there must be a difference in solving the problem. But surely it cannot be a difference in the answer that we will obtain. Else, we are demonstrating that our approach would have been invalid. So, as usual, make our template, and we are saying that the value of m is equal to 2 when the value of v is equal to 3. And we use those initial values in finding the value of the constant. 3 squared is equal to 9. So 2k is equal to 9, and we are multiplying by 2 on that left hand side. Therefore, we need to divide by 2, eliminating that 2 from the left hand side. Being an equation, we need to divide both sides by 2 in order to maintain the logic of the equation that we are actually solving the same equation throughout. So we are actually solving the same equation if we divide both sides by 2, thereby eliminating 2 from the left hand side, and on the right hand side we will have k is equal to 9 over 2. There are two things that we need to take a look at. One, in this particular case, we arrived at the constant easier. 2, the value of the constant is the reciprocal of what it was before. This will always be the case for a direct variation, but not the same for an inverse variation. So what we have right there is a reciprocal of the value of the constant that we had before. But how can we validate the fact that the constant is 9 over 2 on this occasion, whereas it was 2 over 9 on the previous occasion? Why is that so, and why is that okay? We will see why it is so and why it is also okay on a subsequent slide. Let us see if the value of m will be the same as before, because we are solving the same problem by using another method. Therefore, if we arrive at a different value for m, then we have to reconsider and also revisit our procedures to see where we would have gone wrong. So, take our template and we will substitute v is equal to 6 when k in this case is 9 over 2. So what do we see? 6 squared to be equal to 36 and 9 over 2. So there we have 6 squared is 36 and m being multiplied by 9 over 2. Eliminate that constant from the left hand side by multiplying by its reciprocal. We have done that when we did transposition and maybe when we did other tutorials subsequent to that one. So we have, in eliminating a fraction, all we need to do is multiply by its reciprocal, and no doubt we had to do the same on the other side. So 9 will cancel and 2 will cancel, so the reciprocal has guaranteed that we have eliminated that 9 over 2 from that left hand side. And we have 36. And what will we do? Reduce by a common factor. Reduce by a common factor of 9. 9 into 9, 1. 9 into 36, 4. 4 times 2 is equal to 8. The new constant is the reciprocal of the other, but the solution of the problem was just as efficient. We will show that the solutions are related to the two solutions by ratio. Take note that the inverse variation is not as flexible as the direct variation. So we will demonstrate or explain why it is not anything strange that one constant was the reciprocal of the other. And as a matter of fact, we have demonstrated that the answers would have been the same under both circumstances, demonstrating the validity of having written the constant on the other side also. So do not forget that in a variation problem, the constant may be written on either side. It is that when you solve it with this method, the constant that you get will be the reciprocal of the one that you would get if you would have done it another way. We are about to demonstrate the relationship between making use of proportions and using an equation in solving a variation problem. First, let us be reminded of the values of the constant that were obtained in the two cases in which we made use of equations. So do not forget that we had two values for the constant. One was 2 over 9 and the other one was its reciprocal, 9 over 2. What we are demonstrating here is that there is a relationship between making use of proportions and using an equation in solving a variation problem. And we will demonstrate the relationship. And it is, as I said before, the constant is that thing that you cannot forget about when you are solving a variation problem. Its value may not show up, but it is always assumed because when we write an equation, we are equating values of the constant, because that constant is a value that is the same throughout. Therefore, the way that these two are related is the same as how the other two are related, and it is the constant of proportionality that causes such relationship. So let us now look at the first setup in solving the problem by making use of proportions. However, let us include the value that we found instead of the unknown. So we found the value to be 8. I imagine, yes, there it is, 8. So instead of putting the x, we will put 8. So we will use 8 instead of the unknown. And what do? Instead of equating the two fractions, let us find the values of the two fractions. So that is what we did before. We equated saying this over this is equal to this over this. So what we had was 2 over 9 is equal to x over 36. We said that they were equal. Right. That is what we are using. Equality. And equality is caused by the fact that these two are related in the same way that these two are related. And if we do our division, we should get the value of the constant of proportionality. So we are not equating them, we are finding their values instead. So we already know that the two fractions are equal, but we will find their values. So let us find the values on this occasion. So we will reduce the other one by a common factor of 4. 4 into 8 is 2, and 4 into 36 is 9. So we realize that this one is 2 over 9, and this one is also 2 over 9. We see that the two fractions are equal, and as a matter of fact, they are equal to 2 over 9. But how may we have arrived at a constant that is equal to the reciprocal of 2 over 9? So we can go very quickly past this 2 over 9, because we know 2 over 9 was the original value of the constant. How could we arrive at a constant that is equal to the reciprocal of 2 over 9? We have discussed and used time and time again the fact that if two fractions are equal, then if we reciprocate them, they are still equal. The solution of the problem is based on the equality of the fractions, and the fractions are equal to the constant. When we reciprocate the fractions, all we are doing is reciprocating the constant, because the constant is equal to the fraction. So what we are saying here is that this fraction is equal to this fraction, which is 2 over 9. If we invert them, we will get 9 over 2 and 9 over 2, which will still cause them to be equal. What are we doing when we equate or say this one is equal to this one? We are equating the two fractions, or we are equating the values of the constant. So if we reciprocate both of them, they are still equal. Therefore, the problem is still valid, because when we reciprocate the two fractions, they are still equal. The fractions are equal to the constant, then we will still have that constant value in our equation. And that is why a constant or its reciprocal is just as good as the other when we are solving a direct variation problem, as long as we have taken the step in which we should legitimately arrive at the reciprocal. We just do not throw in reciprocal like that and hope that it lands in the correct place. But if we have taken the correct step and we arrive at the reciprocal of a fraction, that we had in the previous case, then we are sure that we have done the right thing, and that is exactly in keeping with the requirements of a direct variation problem. An appropriate question to ask is, so what does the other proportionate solution prove? Which one? This one. What does it prove? Because remember that what we did before was had the bars here and here, in which we are relating values, in which we are relating a value of one of the variable and the corresponding value of the other. But now we are relating corresponding values of the same variable. So what does the other proportionate solution prove? This one we are talking about. What does this one prove? We know that the associated fractions are equal, but they are obviously not equal to any of the fractions that we had before. Let us take a look at the value. Reduce the first fraction by a common factor of 2 and the second one by a common factor of 9. 2 into 2 is 1. 2 into 8 is 4. 9 into 9 is 1. And 9 into 36 is 4. Both are equal to a quarter. They are both equal to a quarter. It is not because both fractions are equal to a quarter why we are able to say that we have a direct variation between the values of v and a direct variation between the values of m. It is because we have a direct variation why the fractions are equal. So it is the other way around. It is not because the fractions are equal why we may say that we have a direct variation. It is because a direct variation exists why the fractions are equal. The fact is irrefutable because the correctness of the answer proves that that is the case. And when we solve a problem using this kind of a setup, we arrived at the correct answer. So we are in no doubt that this approach is also a correct way of solving the problem. So in this particular case, we are relating values of the same variable, whereas we related the value of a variable and the corresponding value of the other variable. The other proportionate relationship proves that if there exists a proportionate relationship between a value of v and a corresponding value of m, which means that all values of v and their corresponding values of m are related in the same way, then there also exists a proportionate relationship between the values of v and the values of m. So let me say that again. The other proportionate relationship proves that if we have this value related to this one in a proportionate way, and this one relates to this one in the same proportion as we had over here, then also because of that these two will be related, and also that these two will be related, which is values of the same variable will be related, values of the same variable will be related, and that is as a consequence of this being related to this one and this one being related to this one. And of course we are speaking specifically about a direct variation. For inverse variation we do not have the same. So the other proportionate relation proves that if there exists a proportionate relationship between a value of v and a corresponding value of m, v and a corresponding value of m, which means that all values of v and m are related in the same way, then there also exists a proportionate relationship between the values of v, these two, and the values of m, these two. This is true for a direct variation, but it is not true for an inverse variation. Whereas in a direct variation, we may relate value of a variable and the corresponding value of another variable, or we may relate values of the same variable. In an inverse variation, we may not relate values of the same variable. We may not, for inverse variation, relate values of the same variable. Let us demonstrate that we may use simple proportions in solving an inverse variation problem. This one is very interesting. We have variables y and x. Y is equal to 3 when x is equal to 2. And do not forget that y varies with x squared, so we will square the value of x. X is equal to 3 and y is unknown. So x is equal to 3 and y is unknown. And there we are again squaring the value of x, which is 3. So square 3, because the relationship between y is with x squared. So there we have it. What do we do? Notice that we do not have any fraction bar. What do we do? For inverse variation, we multiply the corresponding values. So we multiply r by 3 squared. 3 squared is 9. So r multiplied by 9. And we multiply 3 and 2 squared. 2 squared is equal to 4. When we did direct variation, we divided. Now we are multiplying. Why is this so? Surely we will have to take a look at the reason for that by the time that we are through. Eliminate 9 by division. R is multiplied by 9 on that left hand side. Therefore, in obtaining R, we will have to do the opposite of multiplication, which is division. So we will divide by 9 on that left hand side in order to eliminate 9. But we cannot do that on the left hand side alone. We need to divide by 9 on the right hand side also. The 9 is eliminated, and on the right hand side we have 3 times 4 divided by 9. Notice that we did not say 3 times 4 is equal to 12, because we have some fraction reduction to do. So we just maintain the 3 by itself, because we would have to eliminate it anyway. So reduce by a common factor of 3. 3 into 3 is 1. 3 into 9 is 3. So r is equal to 4 over 3 as before. The answer is the same as before. It is not by cookery nor cheating that we multiplied instead of divide. We will demonstrate the reason for this on a subsequent slide. So we are always saying things, and we are always demonstrating the reason for that on a subsequent slide. And everything that we claim, we will substantiate it before we are through with these tutorials. Let us begin by taking a look at a basic direct variation relationship between two variables, x and y. Cannot forget that. As usual, the relationship may be converted to an equation by including that constant of proportionality, which is that constant of proportionality. We have our equation. If we want to find the value of k, we may divide the right hand side by x, and to keep the equation balanced, we divide by x on the other side also. So eliminate that x, because we want to find the constant, the value of the constant. So eliminate the x by division, like that. And then what do we have? y over x is equal to k, rewrite the equation with k on the left hand side. K is equal to y over x. This is why when we are solving an equation that involves direct variation, we equate the quotients of the corresponding values of the variables. Remember that those quotients or fractions are equal to the value of the constant. If not, let us include a remainder. So we are including a remainder that we will divide corresponding values in finding the value of k. Remember what that is? Converting it to an equation. And what do? Use the values that were given in order to find the value of k. That is what we have. And we substituted. Well, we are not including all of the captions. We are just going through the process that we did before. So 2 is equal to k times 9 as we had before. And what did we do? We divided by 9. So there is your catch. In finding the value of k, what did we do? We divided the value that we have there for m by the value of v squared. So we have the value of m over the value of v squared. So turn that around. So what we have there, again, the value of m being divided by the value of v squared. So that is why we did the division. But let us take a second look at something else to cause the entire thing to be a little bit clearer. That is how we were assured about the value of the constant. We also said that equating the fractions was the same as equating the constants. So let us also be reminded of that. So let us be reminded of the fact that equating the constant is the same as equating the fractions, or equating the fractions is the same as equating the constants. Alright, and let us reduce that one by a common factor of 4. So we have 2 over 9 again. Alright, so the constant, which is 2 over 9, was obtained by dividing the values. And dividing the values, that's what we did. Divided the values and equate them. So what we have here is dividing one value by the other, dividing one by the other, and also that is equated to the constant, or that is equal to the constant. So we are showing that if we divide the values, what we will get is the value of the constant, which is what was required. We determine the constant by transposition of the initial direct variation equation. We determine its value and showed that it is equal to the fractions. Therefore, in a direct variation problem, we divide corresponding values of the variables. Right. So notice that when we transposed the equation, what we actually did here was divide the value of y by the value of x. And we show that it is equal to 2 over 9. And when we divided the values here, we show that it is also equal to 2 over 9. And this one is also equal to 2 over 9. Therefore, that is the reason, because we are equating the value of the constants. And the constant is found by dividing one value by the other. That is why when we have a proportionate relationship that involves direct variation, that is why we divide one value by the other. Whereas for an inverse variation problem, we multiply. We will look at the initial setup for an inverse variation problem also. So there we have the initial setup, and no doubt equating by including that constant. So as usual, the relationship may be converted to an equation by including the constant of proportionality. And in finding the constant, we are dividing by that x on that right hand side. So we will multiply by x. So in finding that value of k, we need to multiply the right hand side by x. And to keep the equation balanced, we need to multiply by x on the other side also. So eliminate those from that side. And what do we know? K is the product of x and y. So rewrite the equation with k on the left hand side. What do we have? K is equal to x times y. K is equal to x times y. K is equal to x times y. And remember that in a proportionate relationship, we are equating the values that are equal to k. And we see that k is actually the product of the two. And that is why when we are using the proportionate relationships in solving an inverse variation problem, we always use the product of the two variables, because we are equating values of k, and k is actually and may be shown to be the product of the two variables. This is why when we are solving an equation that involves inverse variation, we equate the products of the corresponding values of the variables. Remember that those products are equal to the value of the constant. If not, let us include a reminder. So go straight ahead. Remember that equation. What do we do? In finding the value of k, include the template and substitute. And after that, what do we do? See, we have 3 is equal to k over 4. We eliminated 4 by multiplication. So we will have 3 times 4, or 4 times 3 on that left hand side. And what is 4 times 3? Actually multiplying the values, or finding the product of the values. And that is what the constant is equal to, the product of the values. Now what we have there is the value of the constant that was arrived at by making use of the inverse variation equation. We will also be reminded that what we have so far is related to the result that we arrived at when we were making use of proportionate relationships. So when we were making use of the proportionate relationships, we multiply those two and multiply those two. When we multiply them, what did we get? Reduce that by a common factor of 3. 3 into 3 is 1. 3 into 9 is 3. We get 12. Therefore, when we made use of the proportionate relationship in an inverse variation problem, we multiply the values and we will get the value of the constant. Multiplying the values, we get the value of the constant, and no doubt the value of the constant is k. And if we take a look at the algebraic relationship, we see that k is actually equal to the product of the variables. Therefore, if we want to equate the constants, which is what we are doing in this particular case in solving the problem by using proportionate relationship, then we need to multiply these two and we need to multiply these two, as demonstrated here. We have shown that when making use of proportionate relationship in an inverse variation problem, we need to multiply corresponding values of the variable. The man-hour is a term used in relation to a situation in which we have a job being able to be completed by a particular number of men in a particular number of hours. Why is it called man hour. And why do we use the man hour? When we are speaking in relation to a problem that involves a job to be completed by a particular number of men in a particular number of hours. Let us consider a problem that involves men working for a number of hours. Although we will not make use of the specifics when we are explaining, we are saying 75 men can complete a task in 12 hours. How long will it take 25 men to complete the same task? This is surely a variation problem between the number of men, M, and the number of hours, H. The question is, what type of variation, direct or inverse? First of all, let us consider what will happen to the values of the variables relative to each other. So if it is an inverse variation problem, we will know. And if it is a direct variation problem, we will know. But let's see what will happen. As it is said, more hands make work lighter. Also, it makes perfect sense that if we increase the number of men, then it will take a smaller number of hours to complete the task, and vice versa. Come on, if we are talking about any situation in which we have people, say for example, we have 100,000 chairs in a building, and these chairs may only be removed one at a time. If we say these 6 men should move all of those chairs, then on every trip we will have only 6 chairs being removed. But if we include that number to 60, on every trip we will have 60 chairs being removed, and hence the job will take a shorter time to be completed. So that is not any part of rocket science that it is very difficult to be understood. As it is said, more hands make work lighter. Also, it makes perfect sense that if we increase the number of men, then it will take a smaller number of hours to complete the task, and vice versa. Therefore, the relationship between the values of the variables will be, as m increases, h decreases, and as m decreases, h increases. Which one of those variations you have, when one goes bigger, the other one gets smaller? And if the other one gets smaller, the next one gets bigger. Well, that's an inverse variation. This, therefore, meets the requirements of an inverse variation. Set up the inverse variation between M and H. So we are talking about the man hour. Set up an inverse variation because it will take more men a smaller amount of time. So inverse variation. So set up an inverse variation and see what happens. Include it near constant right there. And if we want to find the value of the constant, what do? Eliminate that m from that right hand side by multiplication. Right. And what do we get? mh is equal to k, or man hour is equal to k. So k, the constant, is called the man hour, and that is what we used to use a long time ago, the man hour. Therefore, the reason for the problem that involves a number of men completing a set task in a number of hours having a constant that is called the man hour, which is man multiplied by hour, is that it is an inverse variation problem whose constant is the product of the two variables, and that is why we have man hour, or man times hour. Now we will finish up by solving this direct variation problem, and as a matter of fact we will consider a few takes on solving that problem. S varies directly as r plus 1, and we will express that direct variation. So S is proportional to R plus 1. Include the constant as usual. What do we know? S is proportional to all of R plus 1. Therefore, we have to take this constant and multiply by all of R plus 1. So S is equal to the constant times all of R plus 1. If not, we will be in some serious problem if we just multiply the constant by R alone. Use the initial values in assisting to find the value of K. So those are the initial values. S is equal to 8 when R is equal to 3. We have our template there, and we make our substitution where R is equal to 3, but S goes first, and S is equal to 8. R is equal to 3. So do not forget 3 plus 1, 4. So 8 is equal to K times 4. And how do we eliminate that 4 from that right hand side? Well, before we answer, we say, how is it related to K on that right hand side? It is related by multiplication. We will therefore eliminate it by division. So K is multiplied by 4 on the right hand side. Eliminate 4 by division. So that is what we have. And on the left hand side, we have 8 divided by 4, which is equal to 2. So 4 is eliminated from the right hand side, and on the left hand side we have 8 divided by 4 is equal to 2. Rewrite the expression with K on the left hand side. One common mistake that candidates make in solving a problem like this is that they do not multiply all of R plus 1 by K, which is what we have here. They do not do this. They do not take the K and multiply by all of R plus 1. Only R is multiplied by K. So they take the K and multiply by R, and nothing is done with this one. It is not multiplied by K also. S varies with all of R plus 1, and the expression must show this. So the expression must demonstrate that S varies with R plus 1 by taking all of R plus 1 and multiplying that by K, by including brackets as we have right here. We will continue to use the same variation equation. Which one? S is equal to K times all of R plus 1. The value of S is equal to 20. Let us find R. The value of K was found to be 2. So we need to find the value of R when S is equal to 20. But we know the value of K is equal to 2 already. So 20 fits exactly into the slot that is made available for it, and K is equal to 2. What do we do? Well, we have two options. One of them is expand the brackets by multiplying throughout by 2. Or we may make use of the fact that on the left hand side we have 20 that is also a multiple of 2. Therefore, we may reduce the equation by a common factor of 2. So do that. The entire equation may be divided by a common factor of 2. 2 into 20 is 10. And 2 into 2 is 1. But 1 multiplied by anything is that same thing. So we do not need to include that one. So we have 10 is equal to r plus 1. Finally, eliminate 1 from the right hand side by subtracting 1 and keep the equation balanced by doing the same on that left hand side. So on the right hand side we have r accompanied by 1. And how are they related? They are related by addition. Minus 1. Therefore, to eliminate that 1 from the right hand side, we will subtract 1. We have to keep the equation balanced. Therefore, we will minus 1 on the other side also. So 10 minus 1 is equal to 9. And the 1 will be eliminated from the right hand side. So 9 is equal to r, and rewrite the equation with r on the left hand side. R is equal to 9. As long as we understand and maintain that the relationship is between s and r plus 1 and not s and r, we will continue to do the right thing. So we have to declare that the relationship is between s and r plus 1 and not between s and r. After declaring that, we need to demonstrate in the way that we treat the situation that s is actually related to all of r plus 1. And if we do that, then we will continue to do the right thing. Hence, as a result, our answer will be correct. Let us use the proportionate relationship between variables in direct variation to solve this problem. We have variables s and r. S is equal to 8 when r is equal to 3. What do we put? 3 plus 1. Why 3 plus 1? Because we are saying that it varies with r plus 1. So 3 plus 1. When r is equal to 3, we have 3 plus 1. So that is what we have right there. S is equal to 20 and r is unknown. Like that. R is unknown, so we give r the popular unknown x. K is found by dividing the values of the variables in a direct variation. So if we divide the variables, we will get the value of k. But we do not usually write the value of k, but it is assumed. So we divide, and what do? We equate. So we divide and we equate, because the value is a constant. That means if we divide this, we will get a particular value, and if we do this, we will get the same value. Therefore, what we have here and what we have here are equal. But why do we have 8 over 4 here, and yet still we put 4 over 8? And then whereas we have 20 over x plus 1, we have x plus 1 over 20. Why can we do that and be correct? Because if we have two fractions that are equal, when we invert them, they are still equal. And we are making use of the fact that the constant is the same throughout. And if the constant, whether turns out to be in the end a whole number or what, if we do the reciprocal of both of them, they will still be equal. Therefore, we may equate the reciprocal also. And what do we do next? Eliminate this 20 from the left hand side on which we have the unknown. So eliminate 20 by multiplication. 20 will go, and what is the result? X plus 1 is equal to 80 over 8, which we reduce by a common factor of 8. 80 to 8 is 1. 8 into 80 is 10. So we have r plus 1 is equal to 10. And what do we do? Well, now we have it on the left hand side, but we do the same. Eliminate 1 by subtraction. And when we subtract, r is equal to 9 as before.